Yeah, so a lot of our traditional use of supercomputers is simulations, and lately there's increased interest in coupling that with AI. And so before we go through some examples, I wanted to give an overview of why you might want to do this. So we're going to talk about how you might want to have your simulations and AI directly talk to each other. Okay, so one reason could be that you want to use machine learning to decide which simulations to launch. For example, in active learning, you're choosing training data to collect that would make your machine learning model better. In this case, your training data could be simulations or from simulations. And so you could be using active learning to decide which simulations to run. So relatedly, the idea of like design of experiments or experimental design, maybe you're trying to choose a diverse set of simulations to run. Maybe you're trying to choose some that will improve some quantity of interest. So not necessarily that you're choosing simulations that make your machine learning model better, but maybe you're choosing simulations that where you know, something is really fast, or where I don't know, your drag is good. And let's say you already have a machine learning model and you've deployed it. Maybe you're monitoring its performance and say, oh, the machine learning model is getting less accurate, and so I want to collect more simulations to improve the accuracy. And maybe you're trying to sample some space efficiently. So use machine learning to decide which simulations to run that sample that space. And an example from Argonne is this active learning paper by Ganesh Silverman et al. Oh, and I'm going through slides, but the same content is covered in the README of the GitHub repo. Just sorry, I forgot to mention that. So specifically, we're on topic 5, simulation ML, in our workshop README, and then in our workshop repo. And there's this background.md markdown. And so this is like the same content that I'm covering in the slides, but I'm showing it in slides instead, so that I'm not just inundating you with lots of words at once. And so you can click the links to papers, and I have more papers in the README than I do in the slides. Okay. You could also be doing surrogate modeling. So surrogate modeling could be that you're replacing the whole simulation with machine learning, but sometimes you're just replacing part of the simulation with machine learning, like the most computationally expensive part of your simulation, or maybe like some inaccurate part of your simulation, in which case you need the output of the machine learning model to feed directly into the simulation. And here's an example by Romit Malik et al., where we were able to skip solving a PDE because we're using a machine learning surrogate, and the answer feeds into the rest of the simulation. You could also be having machine learning and simulation talking directly to each other because you're trying to skip some IO bottleneck. For example, maybe you run the simulation, then you apply machine learning to compress the results and save the compressed version to disk. Maybe you're doing your machine learning training online during the simulation, like you have some nodes running a simulation and some nodes training a machine learning model based on that data. And so you need the simulation to directly talk to the machine learning, as opposed to wait till the simulation's done, save everything to disk, load it back up for machine learning. And one reason you might want to do this is if your simulation is producing so much data that you were never planning to save it all anyway, but you could take advantage of it now to train your model. And you could also be using machine learning to kind of monitor these long simulations. So you're tracking something that will give you feedback and let you know if you should change something in your simulation campaign. So an example from Argonne is this paper where I think it's JPEG compression of the simulation data, and the machine learning aspect is to remove compression artifacts. And you could be trying to control your simulation with machine learning. For example, maybe the machine learning selects some parameters for the simulation. Maybe it says, oh, this is a good numerical scheme for this case you're in. And an example would be this paper that's also from Argonne, where they're using reinforcement learning to choose parameters for a simulation. And other cases would be maybe you're doing data assimilation. So you're running a simulation, you want to assimilate your data, like to decide good initial conditions for the simulation. Maybe you're using machine learning to do that. So you need the machine learning to directly talk to the simulation. Maybe you know your simulation has some issues, it doesn't cover all the physics. And so you have a machine learning model to learn the difference. This could be called discrepancy modeling, or in a more specific context, could be closure modeling. And sometimes people use some kind of solver or simulation in the machine learning loss function. So you very closely need to keep calling that solver as we're training. So those are all reasons that you might want to have your machine learning and your simulation talk to each other. And I mentioned there's extra links in the GitHub repo, and they're all Argonne examples. So if you have any follow-up questions, there's a good chance one of the authors is around today and could answer questions about how they had their simulation and machine learning talk to each other. Okay, next I want to talk about different ways to set this up. And we're referring to this paper called A Terminology for In Situ Visualization and Analysis Systems. And they weren't specifically talking about AI, but we could use the terminology here. And they say that in the in situ literature, there's a lot of conflicting terminology. And so they're trying to set up some vocabulary for how you might distinguish between these different modes. So one way to describe how you're doing the coupling is the proximity. So do you have the simulation and AI running on the same node? Or are they different nodes, but the same resource? Like you have the simulation running on some theta GPU nodes and the machine learning running on other theta GPU nodes? Or are they distinct computing resources? For example, this Stream MD AI, I think is the name, Stream AI MD, sorry, they have theta talking to Cerebrus. That's one of the links in the repo. And then there's the question of how they're sharing data access. So the machine learning and the simulation could be sharing the same logical memory space, and maybe have to copy data, maybe not, maybe they're just passing references. They could have indirect data access, meaning they each have their own distinct logical memory. And either way, you have to think through how to synchronize the data. And then you can think about dividing between the simulation and the AI in terms of space or time. So in terms of space, that would be like you have different resources for the AI versus the simulation. That means they can run at the same time, but then you have to think through your load balancing, how you allocate some resources to the simulation and some to the AI, and keep them, all the resources utilized, and transfer the data back and forth when they need to communicate. And a different approach would be dividing in time. So you have the simulation and AI running on the same resources, but they like take turns in time. So you could run the simulation for a while, switch to the AI, switch back to the simulation, and so forth. Then there's maybe less synchronization and data transfer, but you're blocking each other. And today I'm going to walk through an example where we did the time division, and then Ricardo's going to talk through an example with space division. And we could also visualize these different approaches in a diagram. And the term loosely coupled might refer to something like this. You have one compute resource, but different processes for the simulation versus AI. Tightly coupled might refer to the case where you have one process that's running the simulation and then it calls the AI. And to draw out this even more loosely coupled scenario, you could have these like different resources for simulation versus AI, and you need to move data between them. Okay, any questions about why you would want to have simulation and AI talk to each other, or these different approaches before we go into examples?
I have a question.
Mm-hmm.
So I can imagine why you would like to have them talk to each other. Say you have some expensive calculation and you are having to do many calculations, and you want to have like a feedback loop with the next calculation and the prediction. But is there a case where this is not a good idea, when you don't want to have them talk to each other?
Well, it could be simpler to run them separately and save to disk. Like you run the simulation, save off the data, and then later load them up for the like to do the machine learning training.
Mm-hmm.
And yeah, depending on your use case, that could be much simpler. And then you have more ability to like keep iterating on the machine learning and trying different things.
I see. Okay, thank you.
Is that okay? So this is what the repo looks like for this morning session. And so we started here with talking about this like background about why we would want to do it and ways to do it. And then we're going to walk through this hands-on example with one approach to coupling Python and C++. And Romit Malik is the one who wrote this example. And then we're going to switch to Ricardo talking about using SmartSim as a different approach. And so we split these two into these folders. So we're starting with this one called Python C++ embedding. And so first I'm going to give you an overview of what's happening in the code, and then we'll walk through running it. Actually, I'm going to show you this diagram. Just 1 second. Okay. So in this little example, we have some C++ code over here, and it's solving a PDE. And we transfer data over to Python to do like some plotting, PCA, train a neural network. And we don't use IO in between, we just directly pass the data. And so we talked about some reasons that you might want to do this. And another reason I haven't mentioned yet is just the convenience of Python. So let's say you want to train a neural network and you want to use TensorFlow and specifically the Python API because it has more features than the C API, you don't really want to like start over and implement neural networks in C++. This could be one reason to call Python from C++. And maybe you mostly work in C++ because that's where your legacy code is, where you have like great simulations implemented, but you want to do some cool analysis, plotting, anything you can think of. Maybe you want to call Python in your C++ code. Okay, and in the repo, further up here, we have a full paper talking about this machine learning approach, but I can give you a quick overview. So we're solving the PDE and we're learning a surrogate model. We apply PCA. So if you're not familiar with PCA, maybe you've called it POD or essentially this singular value decomposition. And you can think of this as a dimensionality reduction approach. So we're applying PCA to the PDE solution to reduce the dimensionality. And then we train a neural network to predict forward in time. And the neural network is in terms of the PCA coefficients, which if you're not familiar, you can think of this as it's in terms of the low dimensional representation. And the neural network is an LSTM. So you've probably run into this before, but if you haven't, it's like a time series model. So we're going to be passing in some time series in the low dimensional representation, predict forward in time, and then you can reconstruct back to the original dimensionality. And this is, Roman wrote this as like a much simpler case for a tutorial. So we're not going to have good results just making it very simple, but you can check out our paper and the code for how we did this PCA plus LSTM with good results. And then it's also, this is a simplified version of what we did in this paper called Python foam, where instead of this simple C++ PDE solve, we were using OpenFOAM, which is a CFD software. So we were coupling OpenFOAM with Python and called this repo Python foam. So if you go over here, it's very similar to today's example, except OpenFOAM. Okay, so in the C++ code, we allocate an array U, and that is the solution of the PDE at one time step. And specifically, this example is Berger's equation. It's 1D, so something like 128 points in space. And we loop over time, solving the PDE for the next step. So that updates what's in this U vector. And we have this collection function to pass the data over to Python. And Python just is going to save it in this 2D array. And it's a global array, so we can keep going back and forth between C++ and Python. Solve one more time step in C++, pass it to Python where it saves it in this row, and then go back to C++. And then at the end, we do our actual analysis. So we call Python. Python does some plotting. It applies PCA. It trains the neural network on this reduced representation. And then it returns 3 rows of V from the singular value decomposition back to C++. And then we print 2 of them. So this is just, I mean, to demonstrate how to have C++ and Python talk back and forth. And to give some context, this is what the data looks like. This is Berger's equation evolving over time. And we start with a sine wave and then head towards the shock. This is what the first three PCA modes look like. And then the LSTM is really bad. And that's just because we stripped down this example and we only had one initial condition for Berger's equation, just the sign. And instead of doing a variety of initial conditions and running lots of simulations. And the other reason it's bad is the training data is from these earlier time steps and the test data is from the later time steps where you're approaching the shock. So you're kind of extrapolating into new physics as far as the neural network is concerned. So as I mentioned, to get good results, you're going to need more training data, and you can see the full code here. Does anyone have questions about the high level idea before I open up the code? Okay. If we go back over here, and we're going to start with theta KNL. And so first you want to grab a node on KNL, an interactive node. I'm going to switch to sharing my whole desktop. Okay, so hopefully you can see my top terminal is this theta KNL, and I grabbed an interactive node already. Is that working okay that you see my terminal? Okay, so you can also grab a interactive node on theta KNL. So this Q subline should look pretty familiar to you. I used a long time just because I wanted to grab it beforehand, before the tutorial started. And this line is in the repo, so you can copy it out there.
Could you increase the text a bit?
Yep. Is that good?
Maybe 2 more notches. Perfect.
Okay. And then next we can source this setup script. And basically we're setting up Python paths, linking to TensorFlow, and we're cleaning up the directory from the last time we ran the simulation, and then run CMake and make. Oops, I forgot to change the directory. And if you haven't yet today, you'll want to run git pull to get updates. We're in the Python example, and we're in theta KNL. Any questions while we let it compile? Okay. While we let it compile, we can look at what the C++ code looks like. We are in C++ and we want to call Python using its C API. And we've got this line to initialize Python. So it's kind of like opening a console for Python. And then this pyrun simple string lets us run a Python command like you would in the console by passing it as a string. And then we also want to link to NumPy. So we use this weird looking command to initialize NumPy. Let's see how our compiling finished. Okay, next we can run this command to run the actual app. And this takes a little bit of time on Theta KNO. So we can kind of switch between watching this and looking at the code. So here we got that initializing the NumPy library. And next, we want to tell C++ about our Python module. And we have to pass the name of the module as a string. And the Python code is under app build. And here's Python module.py. It has two functions in it, collection func and analyses func. And when we go back to the C++ code, so this Py object is the name of the Python module, and this Py object is the module itself. Then we can release our reference to this name of the module, and now we've loaded the Python module. But now we want to be able to call particular functions in the Python module. So here we make another Py object, and we say in this module, there is this collection func, and we're passing the name of the Python function with a string. And we say, oh, we also had a function called analyses func that we're interested in. And now we can release our reference to the module, and we print loaded functions. So if we check on our terminal, we have loaded the Python module, and this is printing from Python within Python module, so proving that we made it over here. Let's see. Oh, yeah, here we go. So at the top of the Python module.py, we had this print statement from Python within Python module. Okay, so back in the C++, we initialize an array U to hold the initial condition for the PDE. So it's an array of the length, the number of spatial points, and we need an extra 2 to handle boundary conditions, but don't need to worry about the details. We have this initialize function that's going to initialize the array to our initial condition, which was a sinusoid, and we make another array U previous, which we initialize to the same. And then here we're down to this loop. We're looping through time to update the solution to go from U previous to U. So solving the PDE forward one time step. Then we have this function to collect data, send it over to Python. So we can check on our terminal. It is successfully calling Python and passing the data over. And now we've finished this, running the simulation, and we're at that analysis function at the end. And we've loaded TensorFlow. We did the SVD, we loaded TensorFlow, and now it's training. that LSTM network. So while that runs, we can go back over to the code. We can scroll down and see what update solution is doing. And this is just doing a finite difference method. So if you've worked with PDEs before, this might look very familiar. And the next time step is related to the previous time step. Okay. So you could, in a real use case, you might have some very complicated simulation here, not just a little short finite difference method. And then we can check out what's happening in collect data. If we scroll down here. So this is sort of like a wrapper around how we want to call our Python function to pass the data over. So we need this tuple to contain the arguments that we want to pass. And we're only going to pass one argument, so it needs to be length 1. And then we say, what's the length size of the NumPy array we're going to pass, which is nx plus 2. That was the length of u. We create this pi object, which is a 1D array. And this Python array is just a wrapper around you. It's not a copy. And we tell it the dimensions that we need. We say it should be float 64, and we say use our array u. And that tuple p-args that we defined up here, we say the first item should be this array that we just created. And then here is where we finally get to call our Python function. So we say, this is the Python function we want to call, and these are the arguments, which was really just this array. And then we do some dereferencing. So this is some like boilerplate around how to call a Python function from C++. And we can check on our terminal and see that the training of the neural network finished. It restored the model, and now it's applying the model to the testing data. So we talked about what happens in collect data. We also have that analysis function, so we can scroll down and see what's happening there. So in C++, we called it analyze data. And this is very similar. We need to call our Python function. This time we don't have any arguments to pass. So it's just a null pointer. So we didn't have to do that whole tuple. We didn't have to do this initial part of setting up the arguments to pass. And it returns p-value. And okay, so this whole p-analysis func in Python is what's running right now. That's where it does the plotting, the SVD, and the neural network training. And we had it return the first two SVD eigenvectors, which was the first two rows of V. And just to kind of demonstrate that we successfully did that, we're going to print them here. And this is a helper function to index in to this array we'd returned. And so we can say we want the 0th row and the ith column. So this little loop is printing out the 0th row of the array we returned. And then we do the same thing to print row 1. And we switch back to our terminal, and we can see that we successfully printed those two modes. Are people successfully able to run this on Beta Kano? Are we having any issues?
It's working for me.
Awesome. Does anyone have any questions?
I actually have a question about when you imported NumPy with the beginning, was that just a lazy initialization, kind of forcing NumPy to do something so that all the backend stuff gets loaded?
I do not remember. Romit, do you know?
Yeah, it's you got it right, basically. So it's we need to be able to access, these capabilities of actually allocating memory as numpy arrays. We need to import it ahead of time. So that's kind of what's happening here. Does that answer your question, or were you looking for something more specific?
No, that makes sense. I just didn't think there might be an elegant way to like, start NumPy or something other than make an array of a -1.
Yeah, it's actually, you realize that actually took us the most amount of time to debug how to get NumPy to behave properly in C++. You see that import array statement over there. So there's many ways you can do it, and there's many ways you can break it as well. So it's probably best not to discuss the finer details at this moment. But we spent a lot of time on figuring out how to initialize NumPy. There's one which does not have the -1 argument. There's one in which there's no import array 1. It's just import array. There's many ways you can call it, and this is something that we found works at least on KNL and GPU. So.
Yeah, you can see here the documentation for the NumPy C API, and I don't remember the nuance thing that this -1 means and the difference between import array and import array 1. It's not the most elegant part of NumPy.
Yeah, it's we kind of hacked it for that line at least. So. Kyle, you're very perceptive. You caught us. Anyway.
Does anyone have any other questions before we try this on Theta GPU? Okay. So I'm going to navigate in our repo over to Theta GPU documentation. And so this is just the same example. We copied app.cpp over here, and under app build is the same Python files. We just wanted to show how to run it in both places. And I have ready, hopefully, yep, over here I grabbed a GPU node. How's that font?
Looks good.
Cool. Okay, so to grab it, I did, a familiar command. Just in this qsub command, you've been doing this kind of thing for the last few days, and it's also in the repo. And I grabbed it for 1 hour. And as I think you're familiar with, first you can SSH into a GPU service node and then run your qsub command. And our approach to setting up Python is different on the GPU. In this case, we decided to use a singularity container. So I think you've seen this week as one approach to get optimized TensorFlow on Theta GPU. So now I'm in a singularity container, and I just had bash at the end. So I have a command line, and we need these proxies in order to access the internet from a compute node. And then we're going to set up a virtual environment. So this command will install virtual env if it's not already there. In my case, it was already around. And then we're going to pick a name for the virtual environment. Where you want it saved. And if you keep this name, you can pick whatever you want. If you keep this one, it'll make our other scripts already be correct. And as a test, I should delete the one I already made. When I was testing the repo. While we wait for that, is anyone having any problems? Okay, so here I made an environment variable to say where I want my virtual environment to be. Now this line is creating a virtual environment in that location. And now I'm going to activate it. So this having an environment variable with the name of the virtual environment was just convenient, so I don't have to type it again. Now we can see we've activated our virtual environment inside Singularity. And I'm going to add CMake. Now, sometimes we've gotten this error, SSL error. So if you get that too, you can change the HTTPS proxy. And I don't know why this works, but we dropped the S. So we just make the HTTPS proxy the same as the HTTP proxy. So I'm going to try this again. Okay, now that I changed my proxy, I was able to add this Python package. Okay, so now I have a Python environment, but I want to pause because I know this may have worked for me and not for other people. Any issues so far? Okay.
Waiting for my interactive job to start. It hasn't started yet.
Yeah. Am I moving too fast? Has anyone caught up with me?
No, we're not like getting the theta GPU allocation. So
Oh, okay.
Oh, okay. It seems like someone's hogging the GPUs. Let me look into this.
Thanks. While we wait, do people have any questions?
Yeah, I'm always a little bit confused about when we need to use a singularity container or not. Do you have any guidance for an inexperienced individual?
So singularity container is one way to get optimized TensorFlow on Theta GPU, and I think that's what NVIDIA suggested to us. And you can also load Conda environments. And Kyle just updated Conda environments. If anyone wants to put that in Slack or chat, I don't have it on hand. Does anyone have any advice you want to pass on about when you use a singularity container versus a Conda environment?
Mostly convenience. Like if I know I'm going to be just trying something out, then I'll grab a Singularity container with the requisite software. But if I want something bare metal long term, typically work with a Conda environment. On a shared resource like Theta GPU, you're often dependent on someone else to maintain those. Or if you're not comfortable with cloning a base Conda environment and installing everything as a user, Singularity is great for like getting things working really quickly. You never really need to use it, I would say.
Great, thanks a lot.
So particularly, I've not used Singularity container much on Theta GPU, but I've always found issues with Conda environment. Do you have any suggestions for it?
So you've had issues with Conda environments when you're not using a Singularity container.
Yeah.
Do you remember any particular issues you've had?
I mean, pretty much a lot of, especially if I want to have my own environment, virtual environment over the module module loaded Conda, and somehow the paths, the environmental paths don't set properly. I don't know, like it's sometimes it works for somebody else, but if I follow the same steps, it doesn't work for me.
Yeah. Let's see. I think we have a page about setting
By
up
the way,
Conda environments.
Theta GPUs, the big job got cleared out, so it should be. Let me know if you're
Great.
waiting in the queue otherwise. Sorry, I was half listening. The Conda environments are tricky, someone said.
Yes, that's what Vernie was talking about. I'm bringing up Slack. Has anyone I'm going to paste into Slack the Conda environment that is most recent. Let me grab it. Okay, so one thing you'll see is that in the documentation, it's doing module load Conda environment from June, but we have a September one that Kyle just put together, and I put the date in Slack. And so roughly you want to load the module, activate Conda, and then you're going to want to clone it to make if you want to make your own custom environment. And so this clone part is important because otherwise you lose the versions of TensorFlow that Kyle included. And then you put the name of your new one, and then later you're directly activating yours. But I know I've talked to Trevor and we've had trouble, and I know Vernie, you've had trouble. So let's see, in this example, we're doing virtual and with Singularity. If people want to put in Slack any particular problems with Conda, maybe someone can help.
Yeah, I can take a look and help. I'll admit it is very error prone, like especially when you're mixing package managers like Conda and pip, and you're cloning, and you might have a virtual env, and you have system CUDA libraries that are all involved. The big thing just to keep in mind is that these shared Conda environments that you're cloning, all the magic ingredients are in building TensorFlow and PyTorch, and so as long as you clone those and use the system libraries, and then you can pip install your own or install your own other simpler packages on top of it, things should work more or less. Oh, and MPI, of course. MPI for Pi can be kind of problematic to build. But yeah, please post any issues with the common environments you have in the Slack.
So now that we've freed up some nodes on Theta GPU, have people been able to catch up? I could also, if you haven't been able to catch up, we could just wait, or I can talk about the Python code.
I'm almost the same place.
Cool.
Yeah, I think we're able to catch up.
Okay. I'll talk a little bit about the Python code. While you get closer to catching up. So as I mentioned, we kind of, for convenience, for demo purposes, had this print statement at the top to demo that you really did get into Python. And then in this case, the approach was to make a global array. So this is a NumPy array, and there's as many rows as time steps that we're going to solve the PDE solver. And this 258 is the spatial dimension. And so here's that special collection func that we were calling from C++. And all it's doing is it's getting past this 1D array that was the next step solution of the PDE, and it's putting it in this global array. And it is using this global variable to keep track of what row it's on. So that's simple, just to like have a demo. And then in the analyses func, that's the Python function that we're calling from C++ at the end after the whole simulation had run. And we do this plotting to plot what the PDE looks like, and that you can look at your file directory, look at the image, and it should match what we had here. This from the README. And then we're performing an SVD. And then plotting the first 3 eigenvectors. So this saves this image, which is the same one here. And saving the eigenvectors to disk. Just as part of a demo. Okay, and then here's the deep learning part. So the training in this example is just the initial part of the time series, and the test data is the later part of the time series. So as I mentioned, this is like a tricky setup because it's extrapolating forward in time into physics it hasn't seen yet. Here we're defining the machine learning model, and this was defined in this ML module.py, which is in the same directory, and then training it, and then applying the trained model to the test data. And then just for demo purposes, returning the first 3 eigenvectors back to C++. Any questions about that? Okay, so back on Theta GPU, we've defined our custom virtual environment. And if you, in the future, you could just activate that environment now that we've defined it. And now we're ready to do this setup script, and I'll open that up because it's a little different this time. Cleaning up the directory again from all these files from last time, and then CMake and make. And it's a lot faster on Theta GPU. I'll just copy this over to my terminal. Oh, I lost my node. And while we're waiting, I can mention that for both Theta KNL and Theta GPU, we also have the non-interactive version. So this submit script is what you could do if you just wanted to submit your job and not grab an interactive node. In this case, this assumed you already created the virtual environment, and that's inside this queue submission. Okay, since we're still waiting, I'll open that up. So the change into the directory. If you've cloned the repo in a different location, you need to change this line and do that cleanup, source the virtual environment, cmake make, and then run it. So this is essentially the same steps as we're doing walking through here, except it assumes that you've already created the virtual environment. So if you've changed the name of your virtual environment, you would also change it here.
There's a question in the chat about actually when you first create the virtual environment, system side packages. That should be like an instantaneous thing because it's not actually copying anything. It's just for system side packages, just like leaves a reference to the original packages, right? Do you remember if the command was like instantaneous?
It was at least really fast. Anyone else having trouble with that line? I think maybe it has been slow for me before, but
Yeah, occasionally just all across the Theta systems because they're all linked together with Lustre. If someone's doing a big, or actually it wasn't Lustre, but anyway, if someone does like a big compile on a head node, it really messes up the latency for commands for other people for a little bit.
that makes sense. Can someone check if I'm close on this queue? Or has anyone successfully finished these steps? So there's just
Yeah, I gave up my allocation, so maybe you might get it again.
okay, thanks. Yeah, we of course have much fewer nodes on Theta GPU than KNL.
The machine's extremely free though. You have another tab open on Theta GPU?
Not right
No.
now, but I could try. Do you think maybe try like single GPU queue instead?
No, I was just gonna qstat the -- start flag. It'll give you an estimate of when your job will start. Just to make sure it's like should be very soon. Otherwise, we can get help from the systems people. Oh, it started. It just as you opened it up.
Awesome. Okay. So let's activate my environment. It's not going to remember the environment variables, so I'm just going to remind it where my virtual environment is and activate it. And then we're going to change directories. That is surprising. So it should know where CMake is because I added it to my environment. Any suggestions, anyone?
You double check which Python.
Is this the command?
So it probably doesn't have, so that you just pip installed CMake?
Yeah.
That probably is just the Python bindings, but it doesn't install the base CMake.
Oh.
Let me remember. So CMake is available on already installed in Theta GPU, and you might be able to access it from the container. Like try, see if this command is available. Or one second.
Oh, do I need to go back in the container and then activate this virtual environment?
Oh, sorry, you're not in the container right now.
Yeah. I think that's the problem.
Yeah.
That's the command for Conda. That should be fine though too. Okay, now I'll activate the virtual environment. And then we need to change directories again. Oh, no, we're already in the right directory. Cool. Great. Okay, so now it's built and we can actually run it. So this is so much faster, even the just getting set up and running the Burgers equation. And TensorFlow automatically grabbed a GPU. Well, or it grabbed all of them. And all right, so it trained the neural network. It applied it to the testing data and passed the first few modes back to C++ and C++ printed. Any questions? Are other people able to run this on Theta GPU as well?
Yeah, it worked for me.
Awesome.
So Bethany, I mean, just a general question, nothing connected to this particular application,
Mhm.
but I can just use load a singularity container then I can just run and source my virtual environment, and then just run any Python file that I want to, and it should work, right?
Yes, that should work.
Instead of all the module loads and stuff.
We didn't need any module loads because we were taking the singularity route.
Yeah.
And like a different route would be the if you're taking the Conda route, then you would do module load for Conda. Is that what you mean?
Right. So, I mean, so all the time I've just tried using module load for Conda,
Mhm.
but I was just confirming with you that if I have just a Python script or an application to run, I can just follow the same step, like loading the Singularity container, then my own virtual environment, and then just I should be able to run any kind of applications.
Yep.
Okay.
And you can think of it as like the singularity container is one way to grab optimized TensorFlow, and
Right.
the Conda environment is just like a different path to optimize
Yeah.
TensorFlow. Yep.
Mhm.
So this is just like not special to this tutorial, just some TensorFlow
Yeah.
environment. You can use it for your own things.
Yeah. Thanks.
I know people get some performance issues sometimes if you try to do big jobs in singularity containers because IO issues. So
Okay. Yeah, good to know
yeah,
that.
it's complicated. You know, containers are extremely popular now, Docker, and then on Singularity on machines, and they're not. You know, they offer simplicity, and like I said, especially if you want to just try something out like this. And then I think
Right.
a lot of people would move to bare metal, you know, like Conda and other libraries eventually.
Okay.
But don't quote me on that. I haven't studied the performance characteristics of containers on HPC platforms.
Okay. Okay, but I mean, it's good to know that's a potential problem.
Does anyone have any questions about this this whole example and this way to couple Python and C++? Because this is all the content. So we got through it faster than last year, and we could move on to SmartSim, or we can talk about this more. We have more
I have a question that maybe it's not so important or relevant, but I got a fairly good result in my test score. The output said I get like 0.99 something, and I think I recall you saying that the way it's set up, you expect to get poor results. So
yeah.
I wonder if I did something wrong or I'm misunderstanding something.
Your results too good. I think the R squared looks really good, and then when you plot the results, they look bad.
I see. Okay, thank you.
So it's kind of a misleading R squared. Anything else? And like I mentioned, if you want to see a more complicated example with this approach to calling Python from C++, you can check out this Python phone repo. And if you want to see a more sophisticated way of doing this POD LSTM, which POD think of basically just PCA, you can check out this paper. And let's see, down here, we put some extra tips for using the Python and NumPy C APIs. Okay, I think we're ready for Smart Sim then. Romit, do you have any comments you want to add about this?
No, I think everything's good.
Cool. All right.
Great. So share my video and my screen. Okay, can everyone see my screen?
Yep.
Okay, perfect. Hello everyone, my name is Ricardo Balin. I'm a postdoc at LCF, and my part of the tutorial is walking you through how to use Smart Sim to do online learning. This could be online training or inference, but also we'll see that Smart Sim allows us to do a lot more. This could be online data analysis or even visualization. So I'll be using the GitHub page to go through the material and then switch to the terminal to walk through the example. So starting from this initial README, I'll take you first to a general description. Smart Sim and the way we're using it, or the way that this example is set up, is a lot more loosely coupled compared to the previous example. I think according to the terminology that was presented earlier, I think it could even be classified as extremely loose coupling. I think this is because this is the case where we have the simulation, or as you'll see in a second, data producer and the data consumer, or the machine learning, actually on separate nodes of the same machine though. So there is a very loose coupling in that case. And from the description page, I wanted to go straight to a few slides where I think the whole infrastructure will become pretty clear. So this is a diagram of what the software infrastructure really looks like. There's 4 components. There's a data producer on the left, data consumer on the right. In the center, there's an in-memory database. This is a key component of using Smart Sim. And then there's also a data producer, a data transporter. This is the part that connects the data producer to the database, and also the data consumer to the database. So let's talk a little bit about these components. First off, the data producer. This is really any PDE solver that integrates a set of governing equations. And so effectively any simulation code, and it can be written in C, C++, Fortran, or Python. This approach is really useful when the simulation is for a transient problem. So the idea is that the PDE solver is successively generating solution states. And these solution states are used to produce instantaneous snapshots of training data, or just snapshots of the solution state to be visualized, or to perform data analysis on. But the idea is that effectively the solution is changing as the simulation is progressing. And the idea is then that the data producer is producing this data and also sending it to the database. This can be done with a specified frequency determined by the problem. So this could be every time step the data is being sent, to see sort of exactly how the solution is changing in real time effectively, or this could be done every 50, 100, however many time steps. An example, I think, to frame the data producers that this sort of software infrastructure was developed for is a CFD solver. And the problems that are being tackled is something like you see here. So these are really complex time and scale resolved turbulent flows. In this particular case, we actually have a flow over a vertical tail of an aircraft. The flow separates, which means that it doesn't sort of follow the shape of the vertical tail, and produces all of these turbulent scales that you see in this picture. You can even just visually see how complex the sort of scales are. And this is just a snapshot, but these scales are time evolving. And what we would like to do is effectively integrate this flow and then send snapshots of the solution to do some learning or visualization or other things. And that's what Smart Sim allows us to do. Now we can move on to the data consumer. Again, this is any program, not just machine learning, but any program that consumes the solution data. It can be written in parallel or in serial, and also it can be written in C, C++, Fortran, or Python. So this really allows to connect really most simulation codes to most data analysis or machine learning or data compression tools. And here I have a few examples because I want to really sort of convey the message that one application of using SmartSim is online machine learning or whether it's training or inference, but there's a lot more that can be done. For example, compute intensive data analysis can be done online. So sort of as the simulation is going with SmartSim, just by developing a consumer that does this data analysis, or data compression can be done, or as I mentioned a few times, even solution visualization. And now the last two components are the data transporter and the in-memory database. And this is really where SmartSim comes and helps us because it provides the ability to do both of those things. SmartSim is an open source tool developed by Cray Labs at HPE. I included the link to their GitHub repo here. I think if you want to learn a lot more about SmartSim, you should go check it out. There's a few examples that they've published using SmartSim already that you can take a look. And then there's pretty in-depth documentation on how to use it. But this is just sort of an overview of what SmartSim can do and how we're using it for this problem. Specifically, SmartSim provides an infrastructure library and then a Smart Redis client library. The infrastructure library is the one that provides APIs to start, stop, and monitor HPC applications from Python. So if we go back to this diagram that we saw earlier, the infrastructure library allows to effectively start the data producer and start the data consumer from a Python script, as well as stop them and monitor them. But it also allows us to deploy this distributed in-memory database that we've been talking about. So the infrastructure library, as we'll see in a little bit once we dive into the code, is really what sets up this infrastructure as the diagram shows it. Then the Smart Redis client is really what is performing the data transport. So it provides clients that can connect to the database from Fortran, C, C++, and Python. So this is how we connect any sort of data producer or data consumer to the database. And then it also provides API that enable this data transfer to and from the database, other commands that allow us to act on data that is stored on the database, for example, deleting that data. But also we can invoke just-in-time traced Python and machine learning runtimes. And we'll talk a little bit later about what that means. But it effectively allows us to use Python runtimes to do more than just delete data on the database, but actually perform some computations on the data stored in the database. So if we go back to this diagram, the data producer now becomes a PDE solver. The data consumer becomes, for our case, a data parallel machine learning program. And then the database here is provided by the SmartSim orchestrator. That's what the database is called. And then the Smart Redis client API is what is performing the data transport. So there's a few features of this infrastructure that I wanted to highlight. First of all, the fact that there is this database between the PDE solver and the machine learning or the producer and consumer really allows for asynchronous communication between these two programs. Asynchronous really means that the data can be transported and it stays resident in the database. So the data consumer, for example, doesn't need to be ready to accept the data or to use the data while the PDE solver is transporting it. Sort of the communication, as this diagram shows it, is independent. So the PDE solver and the database have their own connection, and also the consumer and the database have their own connection. Second, it allows us to store and communicate training data or just solution states for the entire duration of the job. So once the data is sent, it's stored in the database. And so that data can be accessed throughout the entire duration of the job. And it's not just useful for training data, it's also useful for what I'm calling metadata. And in the code, you'll see exactly what I mean by that. It's also because the details of the data transport are sort of delegated to the Smart Redis and their client API. The implementation is relatively easy. So that means that really, researcher has a lot of freedom on what PDE solver to use and what data consumer to use. Once this infrastructure is implemented, switching one of these boxes to the left and right of the diagram is fairly easy. There's also no limit on how many data consumers or producers we have in this diagram. I've just shown one for simplicity, but really we can have multiple data producers, so multiple simulations running at the same time and sending data to the database, or also multiple data consumers. For example, we can train multiple models from the same data at the same time. We can train a model and then also perform visualization. So there's a lot of freedom there. And then finally, SmartSim allows us to do model inference. So evaluate a model that has already been trained or is in the process of being trained, also as the simulation is running. So there's a great example of this on the Smart Redis GitHub page. And the idea here is that there's no longer a data consumer. So the picture just focuses on the left half of it. And effectively, the PDE solver is evaluating a neural net model to determine quantities needed to keep integrating. So there's data transfer between the solver and the database, in that case, not to do training, but to evaluate a neural net model that requires, let's say, its own resources to be evaluated. Cool. So now I meant to go back to the specific example, but I wanted to pause here for a second to see if there are any questions about sort of the general picture of what this infrastructure looks like and what the example is going to do. Okay, cool. So the second paragraph here in the description is basically a summary of the slides. So if we scroll down, there's basically a little bit of description about the specific example that we're going to tackle. So the picture stays the same, except that for this example, we're not really going to be using a PDE solver. Effectively, we created a simple Fortran function that emulates what a PDE solver would do. So it's basically generating training data in an iterative manner. So there's a loop over time steps, although these are not real time steps. And at every time step, new training data will be created and sent to the database for training. And the specific sort of, let's say, function that we're training, it's not, a model for some physical quantity, but it's just a simple polynomial function. So this Fortran routine that you'll see in a second that acts as the data producer is basically just going to pick some random numbers along the domain of this polynomial, evaluate the polynomial, and send both the inputs and outputs, so the x values and the f of x values, to the database for training. And then the data consumer is a data parallel machine learning algorithm. This is actually, it's a simple model. We're just trying to learn a polynomial, but this is actually very similar to what can be used for a true online learning application. Here's a little preview of what we'll see once we run the example. And we'll see that we can train a model that predicts this polynomial reasonably well. And this will be done online, and most importantly, without saving any data to the disk. So that point should be very important. And I should have maybe prefaced with this. So this infrastructure is really aimed at the problem that was mentioned earlier, where the simulation would be producing too much data for it to really be saved to disk in order to do learning offline. So in a separate instance from the simulation. So this approach is really sort of trying to solve the problem where we need to take advantage of the simulation running and producing all of this data for the learning. Otherwise, saving multiple snapshots of very large simulations would just take up too much disk space. Now we can head over to the example. So now we're going to go look at this machine learning Fortran Smart Sim directory. And here we have another description. I think I would like to walk through the code and how it's set up a little bit before moving on to the example, so we know exactly what's happening, especially since we have a bit of time. So let's do that first. We'll go into the example. And here you'll see a few scripts. The first one, just clean directories, just used to clean the directory. So you start sort of from scratch every time you run a new problem. And then there's a run and submit script. So the submit script allows you to submit a script job, but we can do this, and we will actually do this for the tutorial as an interactive job. So I think you're pretty familiar with how these submit scripts are set up. So I won't go into too much detail, but I did want to focus a little bit on this run.sh script. So because we are doing machine learning, we're using Python as our the programming language for our data consumer. So we do have to load a Conda environment. There's instructions in the README that you saw previously, and we'll go back to it, about how to build the Conda environment specifically to use SmartSim, but it does take quite a bit of time. So I have built one already and placed it in this location here on Theta, which you should all have access to. So the example is set up to use this environment. So there's no building of the environment that you have to do for this example, but there are instructions in case you want to build your own, so that then you can test SmartSim out. But this run.sh script is effectively grabbing some information about the size of the job that we're given in the submit script. It also sets up, the environment. We switch from Intel to GNU programming environment, export some variables, and then this is the Conda specific part where we load mini Conda, particularly this latest version from July, and then we activate the environment that was prescribed at this path right here. And we'll see that this run.sh script is effectively just running Python, and it's running this driver.py script. And we'll take a look at what that does right now, because the driver script in this src directory is actually what is using that infrastructure library that I mentioned. So there's a little bit of grabbing of the inputs passed through the command line. This is a function to get the node list of the job. So if we, as you'll see, we'll submit a job with 4 nodes. So we need to figure out what nodes we were given by the scheduler, and then assign nodes to the database, to the simulation, to the machine learning. So this first part of the code does exactly that. And then these last 3 sections are the ones that are using the infrastructure library APIs to, in the first section here, launch the database. In the second section here, launch the data producer. You'll see that this is a Fortran executable. And it then launches the data consumer. And this is a Python code that does the machine learning training. And then finally, we stop the database. It's relatively simple. It's just a matter of understanding how to use these APIs, and the SmartSim documentation does a great job on explaining exactly how to use those. But one thing that I wanted to mention is this argument here for this start routine. So this is the one that launches the data producer and the data consumer. Because this block false effectively means that the driver script is able to launch the data producer and then keep going with the script. So this sort of command does now become a blocking command. And this allows us to launch data producer and then keep on going and then launch the data consumer. But you'll notice here that for the data consumer, we did have to put block is equal to true. That means that then the driver is sort of hanging right here at this line until the data consumer and the data producer are done running. And once that happens, then it's allowed to keep going and then closing the database, the orchestrator. Otherwise, we would be closing the orchestrator before the data producer and consumer would be done running. Before I go into the Fortran and Python codes, are there any questions at this point? Is everything clear?
So Ricardo, I
Sure.
just had a quick question. So Are you saying that if at all for any reason the consumer is done finishing its job before a data is produced? I know that the scenario might sound stupid because it's more for a environment where the data is just flowing online. But
Mhm.
for any reason, if there is a larger time gap between successive data that is being produced, so does the driver just shut down this whatever system, or is it like waiting for the new data?
So actually, we'll see in a second. Basically, the driver will keep running until the machine learning is done learning. So the training is complete. So of course, there's a scenario where there's sort of a bug in the code and the data consumer can crash. In that case, then what will happen is that the driver will then go to close the database, which then will make the data producer also crash because it can no longer send the data to the database. In that case, sort of the entire, I would say, infrastructure has a bug and crashes. But you'll see that the data producer, in this case, serves the purpose of the learning. And so it really is waiting on the instructions of the data consumer to tell it. And that's, you'll see how I'm using sort of metadata to communicate between the two programs. So the idea is the data consumer is basically in charge of how long this job runs, because the idea is to train this model. So of course, there's a case where it takes longer than the allocated time on the machine. And that's something that can be sort of coded in. That is, if the time is about to run out, we still pause the training and save checkpoints so that we can repeat this process. But the idea is that the data consumer will really be sort of driving how long this simulation runs, or this entire job runs. And the data producer keeps running and keeps sort of iterating, sending new data until the training is complete. In another scenario, for example, where you're doing visualization, you would basically be switching the data producer and consumer. So in that case, the consumer is really just there to provide, a visual figure of the simulation. So in that case, it's the simulation that's driving how long the job runs. And once the simulation is done, then only at that point, the visualization will also quit. And then sort of both programs quit sort of simultaneously or one right after the other. And then both exit cleanly, and then the driver also exits cleanly. But I think you'll see how exactly that's done through communicating tensors through the database in a second.
Okay, yeah, thanks.
Sure. Any other questions? Okay, so going back to this SRC directory, sorry, you'll see this load data.f. So this is the Fortran routine that is basically doing the data production. It's a parallel routine, and you see that MPI init is called pretty early. So the code that we're going to be looking at from this point on is executed by every rank of the data producer. So the first step is to initialize these smart Redis clients. This is hard-coded for simplicity, but we fixed the number of database nodes. So basically, how many nodes of Theta is the database running on? In case it's hard-coded, simply because two different commands need to be called, or the argument changes whether it's one or more than one database node. And then we move on and set up some, let's say, set up basically the size of the problem. So how many samples each rank is going to produce of training data, how many inputs and outputs do we have? And then you'll see that the first thing we do actually, one of the first things we do is send this check run array. So this is just a simple array of 1. And what this check run is used for is actually sort of an array that will stay in the database for the duration of the job. And then this is the array where if the value changes, then that's how we communicate whether the training is done or the simulation is done. And so the other program needs to close cleanly when one of them is done. And then the next thing we do is we can send some of that information on the size of the problem. And sorry, I should have pointed out, this is the line that is used to send the data. So you can see here, we're using the Smart Redis client API to, as the name says, literally put a tensor onto the database. So you can see that this data transport is really sort of made pretty easy once we can use these API. So after sending some information about the size of the arrays, we generate the keys. Another thing you'll notice is that one of the inputs to the put tensor routine is this size, it is a string. And this is called the key of the tensor in the database. So effectively, this means that every tensor is identified with a distinct key so that you can send data without overwriting what was previously being sent. Or if you send data with the same key, you actually do overwrite the data. And what every rank is doing is it's actually creating a key that is distinct both for the rank number and also for the time step number. So this was done intentionally so that every time that the data producer is sending data to the database, it's not overwriting what was previously sent. Now, of course, if you keep this process going forever, you'll end up filling up the database with snapshots of your solution or training data. But I did this intentionally for this example problem to show that you don't have to send and sort of store only one snapshot at a time. You can store as many snapshots as really the database allows you to store data in memory. That means that your training doesn't have to be done on one snapshot of the solution only. It can be done on multiple. So, you know, after you receive the second snapshot, say to the database, the machine learning can pause, and instead of taking only the second snapshot, can actually take the first and second. So this will allow you to use sort of a data from past time steps for training. And then the Fortran just sets up a simple loop over time steps. We sleep for 10 seconds. This is simply because otherwise the training data would be generated very quickly. And I wanted to simulate, you know, sort of the time it would take for a code to solve some PDEs. And then you see the first thing we do is we go grab the tensor that determines whether we can keep running or not. So if the value was set to 0, so in this case less than 0.5, then the iteration loop will actually exit and the program will stop cleanly. And you'll see that in action in a second during the example. And then we just generate our training data. I apologize for the color. The interpreter doesn't understand that this is not a string. Here we are adding just the time step number to the key of the tensor. And then in this block of code, we are sending the training data, again, using this put tensor routine. And then finally, what we do is we send also the time step number to the database. This is actually what is used by the machine learning program to determine whether new data has been sent or not. And we can actually go take a look at that right now. So if we go to train.par.py, you'll see that the sort of setup is very similar. We import the libraries that we need, and then we initialize RVOD and MPI for PY. So again, this code is executed by every rank of the machine learning. We initialize, in this case, the Python clients in the same way. And then here there's some details about the specific neural network that I'll skip for now. But here you'll see that we go grab using, again, this Smart Redis, in this case, Python API with get tensor. We grab the information about the size of the arrays that the Fortran program sent. And we can use those as variables throughout the program. Here we set some hyperparameters for the training. And then I'll just skip to the sort of salient part of this, which is sort of this while loop. While loop is not the prettiest thing to do, but the way that we've set up the driver, launching the data loader first, we've seen this while loop to be pretty stable. It doesn't hang unless there's a bug in the data producer. And the first thing it does is you'll see that it checks and it goes to grab from the database the time step number. Now, if the time step number is that it just grabbed is different from the one that is currently saved in this program, then that means that new data is available. So that means that we can go grab the data from the database and then train with what is now available to train on. Otherwise, down here, we go to the else part. That means that new data, if the time step number is not different, so it's the same, that means that new data was not made available by the data producer. So that means that we can train and perform another epoch on the data that we just loaded. And I won't go into all the details on how exactly we grab the data right now. We can do that later, but I wanted to make sure that we have time to go and actually do the hands-on session. But it's this part of the code right here that goes and grabs the data from the database. Actually, sorry, no, that is just setting up the data set and distributed sampler and loader. I'll just give a quick reference. This is actually how we are grabbing the data from the database. And I can explain this line in more detail in a second. But I wanted to make sure we got to running the example. So if we go back to this example directory at the GitHub, we'll see we have these 3 scripts. And these are the ones that you'll see now when I move to my terminal and go to that location. Here's just the most recent pull of the GitHub repo. So we can move into the example subdirectory. And I guess before running this, I can ask if there are any questions at this point. Is sort of what we're trying to do clear and how we have a data producer that is going through iterations to produce this training data, and then a data consumer, which is the training, and that is sort of grabbing the data from the database as it becomes available and performing training on that. Okay, cool. So then what I will do is go back to this README file here. And here we'll find some instructions on how to run this, this example. So I already submitted an interactive job on theta KNL. So I already executed this command right here, but you'll want to do that if you have not done so already. And then what I'll do now is I'll go build the Fortran data loader, or sorry, data producer. So that will be this terminal here on the top right. So we move to the Fortran and then example and into SRC. So in this directory, you'll see that we have basically the source codes. So we have the Python, the Fortran routines, the driver, and also we have some helper configuration files to build the Fortran program. So the first thing to do would be to source this env theta script. This basically sets up the environment on the terminal so that we can build the Fortran program. This, for me, just means that I've run this environment script already. So there's no Intel programming environment to switch from Intel to GNU. But that's just because I've run this already. And then the next thing we can do is we can run the config file. When we do that, we'll basically be building the Fortran executable that will be performing the data production. This shouldn't take very long. This is instead the directory well, where we can run the job. And one thing to note is that maybe while that's code is building, I can go back to this. You'll see from this queue subcommand that we're actually asking for 4 nodes. This is because in this particular example, we've chosen to have 2 nodes for the data producer, 1 node for the data consumer, and 1 node for the database. So that's a total of 4 nodes, and we have to request for all 4. But if you use this example and change some of the inputs, which you can certainly do, and there's some notes on how to do that here in this README file, you can change how many nodes you are assigning to each of those 3 components. You can have 1 node for each or multiple nodes for each of those components. So the next thing I'll have to do is execute this run.sh script. So I'll copy this command over here and wait for the Fortran program to finish building. It is taking a little longer than usual. Okay. Okay. Okay, so before I start running it, is everyone sort of caught up? Are we ready to run this together, or should I be waiting for a few people to get set up on Theta KNL again and build the Fortran executable?
Can you go through like what you did on the theta login node?
Sure. So I basically just, if we go back to the GitHub, I basically executed this first step of the description. So I CD'd into the example and then src directory. And then the idea is to first set the build environment for Theta. And that's done by sourcing this env theta.sh script, which we can take a look at. And you'll see that it effectively is just switching from the Intel to the GNU programming environment. It's loading CMake and then exporting this environment variable that is needed to build the Smart Redis client. And then the next step, going back to the GitHub again, is to actually build the code. And we can do that by running this do config.sh script. So we go back to the terminal here, and we can take a look at it. And it's basically just calling CMake. It's setting our C and C++ and Fortran compilers, and then it's just setting some flags. In this case, I told it to build in debug mode. And then it's just calling make. And then finally, make will execute the instructions inside of the CMake list.txt file. And this is getting into some of the details of CMake, but the idea is that we also need to build, along with our Fortran data producer, we need to build the Fortran Smart Redis client API. And so this is sort of the part where we go grab those files. And those files are the directory containing the Smart Redis client is actually sort of cloned from GitHub as you install the Conda environment. So for everyone, it'll be accessible at this path that I mentioned earlier, also where the Conda environment is. But if you decide to install your own, you'll also have all of these files available. So what you have to do in that case is just basically change this path so that you can go grab the right Smart Redis source files. And then finally, it just builds the executables and links the libraries. Does that help?
Yeah, thanks. Yeah,
okay,
thanks.
Sure. Cool. So let's run this. Here we are effectively giving the inputs that I mentioned earlier that are inside the submit script right at the command line. And they're sort of summarized here. It's basically outlining how many processes per nodes we want to use, how many database, simulation, and machine learning nodes, and then how many processes for the simulation and the machine learning. These other two, I'll do this, which is a way for us to take a look at what is happening to the data producer and data consumer. So you'll see those two terminals populating in a second. Okay, so here we've parsed the node list, and it's telling us exactly what nodes each of those components are running on. We see that we have the database running on one node, and that's going to be node 4000, simulation running on two nodes, nodes 4001 and 2, and then the machine learning is running on one node at node 4009. And now we're seeing that the driver is starting the database. Okay, so that's done. It's now launching the data producer, and now it's sort of stuck at this launching the data consumer part. What you'll see coming out of here are just sort of monitoring those jobs. So you'll see when they're running and when they're crashing. But on this terminal here on the left, what you're seeing is that this the data producer sort of starting the iteration. It did some of the things we talked about, initialize the clients, sent the size information of the training data to the database, and now you'll see that it's iterating through those time steps and just sending the data to the database. This is the key that it's using to send the data. So the machine learning program takes a little bit longer to boot up. So effectively what is happening is we're having the database sending data to, the data producer sending data to the database that is not currently being used to train on, but that's okay. We should be seeing this start running any second now. Okay.
Hi, Ricardo.
Hi.
Maybe you could look at the train model R file.
I can.
That's where the output should be.
No, I think for this example, I put it in the output file. It seems like it's just taking a long time. It's usually always slower than the data producer to get going, but doesn't take this long. And you see here the infrastructure library APIs are telling me that the program is running. So I think maybe it's trying to connect to the database. That's taking a little longer than usual. Okay. Yeah, because I'm not even seeing the output that the if you go like to here, not even seeing a print statement that it's initializing the Python clients. So it's still trying to, I think, perform the input of, oh, okay, perfect. Yeah, it just was taking a very long time. Really isn't usually this long. You can see, so here on the data consumer side, we are getting this these initial outputs saying that we've initialized clients and received some of the data. And now we are getting new training data from the database because when the program got to this point, time step 20 was the last one that was sent to the database. And you see now that then the program starts the training. And you see here from this output that it's actually doing between 3 and 4 epochs for each, let's say, snapshot. So 2, 3, and 4 were done on time step 21. Now after 4, it realized that new training data was sent to the database. So then it loaded time step 22 and then kept running. So if we scroll down this output, we'll see the loss, decreasing. The model is getting trained. And then at the end, you'll see a little bit of output saying that, actually, I guess we haven't quite converged yet. Okay, now we have. What happens is that we've met the convergence tolerance, which I just put as 1 for this simple example. So that means that we're stopping the training loop in the machine learning side. We save the model to the disk. And then the machine learning program is also performing just some quick predictions on that model so that we can produce that figure that I showed earlier. Once that's done, it's then telling the data loader to quit. So you'll see on the left here in a second that the the data producer got that message. Again, it was done using that run check sort of metadata tensor. So now both programs have finished. You can see that here on the driver, that both programs here, the load data and train model, were completed. And then the driver was able to stop the orchestrator. And that's how the job ends, basically. And then if we take a look at what that produced, it produced a series of files. So there's some files that specify the details of the database. But really what we would be interested in, this load data.error and .output. These are effectively the outputs that we were seeing here in these two terminals, and it tells us how these programs executed. And then train model.out is effectively what we were looking at here on this terminal on the right. But what this also produced is this fig.pdf. So I can't visualize that on Theta, but I can just do a quick copy to a local machine and then visualize it here. And here we go. And we're producing a figure very similar to the one that I initially showed. So this tells us that we were successfully able to train the simple neural net online. And hopefully it's clear now a little bit more about how the driver is sort of hanging right at the machine learning program and waiting for it to finish the training. Once the training is done, then it's the machine learning program that actually tells the data producer that it's time to quit. And so then you'll have both sort of applications quit, and that's reported here in the output of the driver, and then it can move on to then quitting the orchestrator and the database. Is there any questions about that? Or anything else I can answer, or things that weren't clear?
You might have mentioned this, but is it possible to set it up so that the machine learning part does not have the ability to kill off the simulation, the producer?
Yeah, absolutely. So basically, if we go back to the Python code, you'll see here, for example, that right. So here we're breaking whether we reach the maximum number of epochs or the tolerance. We get out of this sort of while loop, which was sort of the training loop, and then saving the model to file. We go down to the very bottom. We are basically sending with this put tensor call an array of zeros for that same key called check run. So then just by not performing this call right here, basically the simulation doesn't know that it's time to quit.
I see. That makes sense.
So that without this line right here, the simulation would keep running until basically it's done with its with this loop over time steps. And one thing that I wanted to mention is you can take a look at the submit script. And this is really where you can sort of have the freedom to scale this problem out to effectively as many nodes as you want. So we have here specifying the number of nodes for each of these three components, but there's really nothing stopping us from having, 2 nodes to perform the machine learning. And of course, then in that case, the machine learning would be performing a lot faster than what we've seen here. So it maybe would be able to do just 1 epoch for every time step of the simulator. And similarly, we can scale the simulator up or down to also sort of change the frequency at which it's producing its training data. And then lastly, we can launch databases on multiple nodes. There's just a sort of a quirky feature where you can't run with 2 database nodes. So either 1 or we have to skip to 3. But once we are at 3, then we can scale up to even hundreds of database nodes. And so that would be the case where you really need a lot of memory to store all of that training data. But sort of infrastructure, we've tested it on Theta and it's quite scalable. So it's really set up to tackle sort of full simulations that need to run on leadership level machines like Theta. And then there's also, last thing I'll say, unless there's any more questions, everything that I've shown is for Theta KNL, but there's nothing stopping us from moving to Theta GPU or other GPU machines so that the training can be done on the GPUs. The reason why we haven't shown that in this tutorial is because we personally are still setting up the environment and building Smart Sim on Theta GPU. So just that process wasn't ready for users to just cleanly be able to execute a script like we've set it up for Theta. So that was the only reason why we didn't show that. But it's of course, it of course can be used on GPU nodes as well.